so last time we did Brent's proof for formula reduction of depth in the case of formulas. So depth can be reduced to log s. That was our result. And we noticed that for the case of circuits that proof will fail. So now we will give a different proof, give a new proof based on degree as a potential function instead of size. So this is a theorem by VSBR. Quite old already, from 1983. So they showed that if you have a degree D polynomial, with size as circuit C, so let degree D polynomial F have a size as circuit C, then so although in the assumption in the hypothesis there is no mention of depth, which means that the depth can be as high as size, what we will show is we will give an algorithm, a constructive way to reduce the depth to log D, and size will not blow up by much. So then there is a polynomial in S. So okay, forget n because that is contained in S. S log D size order log D depth. Circuit C prime that also computes F. Again, proof will be mostly constructive. So degree D here can be arbitrary, so it can be as high as S to the S in the case of circuits. Like these are general circuits, but the depth will reduce to log D, and accordingly the size will grow. But the growth in the size will be dependent on only log D, not D. Okay, so this is actually applicable to also exponential degree polynomials. Yes, this is much stronger than homogenization result. It is actually efficient for exponential degree polynomials also, as long as there is a small circuit computing it. Is the statement clear? Okay, so this is very different from formula, and the proof will be long and technical, but the idea is to work with the degree as a potential function. So without loss of generality, assume that C has Fanon 2 and that C is right heavy. So right heavy will be defined as for every gate V in C, degree of the left child VL is at most degree of the right. Okay, so that's the left child and right child. Yes. So this is without loss of generality, because we are assuming fan in to be 2, and if for any gate, for some gate, if degree on the left is more, then you just swap. So this you can do efficiently also. So we'll call it we'll assume that the circuit is right heavy. Okay, heavy in terms of degree and not size. Okay. This proof exposition is not following VSBR. We will follow the exposition given in a survey by Ram Prasad. So that is available online. We are following that exposition. But the main idea is because of, same as in VSBR 83. So by this notation square bracket V, we denote the polynomial computed. At the node V, at gate V. And so you should think of the proof as building a circuit C prime step by step, looking at C as you walk down from C, from the root to the leaves. And in C prime, the nodes that we will put will exactly be the square bracket V type. So this will also be a node simultaneously in C prime. Will be made a node or a gate in the new circuit C prime. Okay, so this square bracket V has two interpretations. This is happening in parallel. C prime is being built as we are analyzing C. So as we have seen in the previous proofs in derivatives and also in Brent's formula depth reduction, we had some notion of identifying a subtree V and removing it from the tree and replacing it by a new variable. So we'll now formalize it in terms of quotients, quotienting process. So for gates UV, define gate quotient as so U by U should be defined as 1. For a leaf U, and a different gate V, you should define U by V as should it be 1 or should it be something else? Well, V is unrelated to U, so it should be defined as 0. I mean, the idea would be that if V appears below U, below the gate U, then the quotient should be the thing which intuitively you should get if you divided U by V. Kind of, yeah, not the remainder but the quotient. So ignore the remainder and look at the quotient. If you expanded U in terms of V, so AV plus B, right? So the A is what we want to compute. So in this case, it should be defined as 0. And you can do this arithmetic So if two gates are being added, then quotient by V should be defined as, so we are now inductively going upwards, right? So if you know U1 by V and U2 by V, then the sum should just be the sum of the quotient. So this is the definition, inductive definition, and also a property. And finally, you might face a multiplication gate. What should you do then? Yeah, so intuitively you should quotient only one of these, U1 or U2. It's one side, yeah. Doesn't make sense to quotient both and multiply intuitively. So we will do this. Okay, so we'll quotient the second one, the right one.
What is bracket U1?
Oh, bracket U1 is just U1, whatever U1 was computing. So U1 is not changed, just U2 is changed. So this is essentially the definition of quotient for all the gates. It's an inductive definition, goes from leaves to the root, level by level. So looking at this definition, what are the immediate properties? What can you, okay, so first of all, this is a polynomial, right? We are calling it a quotient, but this is not a fraction. It is always a polynomial. Is that clear? Because base cases it's 1 or 0, and then when you are adding, you obviously get a polynomial, and the multiplication gate also gives you a polynomial. So this is always a polynomial, so you can talk about its degree. What is the degree of this polynomial U quotient V? So I don't know it exactly, but at least the upper bound is the difference, right? So this cannot exceed degree of U minus degree of V. This again follows just inductively from the axioms.
But when you quotient U by itself,
Yes,
then degree U minus degree V is
0.
0.
Yeah, right.
Oh, but okay.
Yes, that is consistent with our norms, and it is also consistent with if degree of V is strictly more than U, then the RHS is a negative number. Left hand side also we can understand it to be negative degree because U quotient V is 0. So 0 is somehow special. Its degree is not 0 but negative, which makes sense. Right, the other simple observation is if V does not occur in the tree rooted at U, okay, so you look at the subtree under U, and if V is not a gate there, then U quotient V will be, that will be 0. This is just an extension of this leaf property. So just proof sketch. So in the induction, base case is that of a leaf. So you will induct downwards starting from U, and ultimately you will reach a leaf, and you will still not have found V. So you will get 0, and the 0 will just add and multiply, give you 0 at the top. So this you can complete, it's not difficult. Let me skip the proof. Any questions at this point? So these are the tools that we'll use now a lot in the proof. Okay, the proof will really develop on this quotienting idea. Let me write down again the intuition for the quotient. say in the subtree of U, under U, V appeared, so U will be A V plus B. So the intuition behind the quotient definition is this U quotient V should be, so this is for some polynomials A B. So we would like to talk about the circuit that computes A. But in this tree computing U, it is not immediately clear whether A was computed, right? So maybe A and B and V were all computed together. So it was all mix and match. So A may not have been separately computed, right? So this is why we need a new notation to talk about A, and that is exactly U quotient V. So this is formally obtained by U quotient V. Okay, you can see that this actually equals A. Is that clear? Well, this is assuming that V is on the right. Because in the axioms of quotienting, when we have a multiplication gate, we are preferring the right side. So V should appear in the tree of V on the right as a right child of its parent, and then you can see inductively that the claim U quotient V equal to A is correct. Okay, so this is the sole intuition behind the quotient operation. So the circuit may not be computing A as an intermediate polynomial, but still we can refer to it by this operation. Right, so if you think of U as the root, then what are the V's to look at? Right, V refers to all the gates in the circuit. So which of these V's are good for our algorithm to reduce depth? So those will again be frontiers. Okay, so we define that frontier gates. So the frontier at degree M is the set of these gates V that has to be the case. Degree of left child will be less than or equal to degree of the right child of V, which should be strictly smaller than M, and degree of the parent V should be at least M. Okay, so simply put, it is just those frontier at degree M are those gates where the degree of the polynomial computed is at least M, but the children it is smaller than M. Okay, so that is naturally the frontier. Right, the first time it crosses M or it falls. Yeah, so V is the gate where first time it is crossing M as you go from leaf to root. So that's FM.
When you go from the leaf to root, the degree won't change monotonically, right?
Oh, but somewhere it has to increase.
Yeah, but it could, on the same path, it could increase and then decrease and then increase again. Right?
But then moving it, then start to.
But
I'm
then
no-
the
I'm
probability
not-
of the circuit can be very large, right?
No, I'm not sure we want to do all that. The definition of frontier stands as it is, as mentioned, as written here.
So during this induction, we are going from the top to the bottom, right?
Yeah, I think
At some point, we can just stop and then
right.
get our frontier.
Yeah, so you look at the frontier as the node closest to the root, closest to root or this u. Let the degree fluctuate, but the one that is closest to the root is better. Actually, closest, yeah, it will not matter. Actually, let me define it as deepest, closer to the leaf. So Fm are the deepest multiplication gates with degree greater than equal to m. So put this in the definition. So Fm will be the deepest ones. So once degree m has been crossed, maybe later on it will fall, but we don't care about that for now. Let us see in the future if there is a problem we will redefine. And the other thing is that it has to be a multiplication gate. Is that clear? In the definition it was any gate V, but if the degree is increasing, then it has to be a multiplication gate. Addition cannot increase degree. So these are the deepest multiplication gates. Think about them as. So now if there are two gates in the frontier, what can you say about the quotient? Right, because V cannot be in the subtree of U, right? So that's 0. That's almost by definition. V is not in the tree rooted at U, that's all. Because if it was, then U won't be the deepest. Right, so now for the root U, we have these frontier gates. So we want to expand the root using the frontier gates. Okay, so we'll write something called the frontier expansion lemma. So suppose U is a node with degree at least m, then you have this identity in using the frontiers. So since U has degree at least m, somewhere in the tree at U, degree must have crossed m, because at the leaves the degree you start with is 1 or 0. So somewhere there was a jump, and so that gives you at least one frontier gate W. So with respect to this, you can quotient. So U quotient W will be a non-zero polynomial. You multiply that with W and take the sum. Okay, so we want to show that this sum will come out to be U. if you go over all the frontier gates. So this is a slightly non-trivial statement. Okay, so let us prove this. Actually, I want to make more statements. So that is one thing. In the lemma, we will also say that if the degree of u, well, it is m, at least m, but there is a gate v with degree smaller than m, then the quotient of u by v, this will be consistent with the above formula in the following way. Okay. So we have the original formula of u, and that we can also quotient by a v with a lower degree, and this would be the change. Is the statement fine? So we'll prove these two things in the same way. And obviously it will be inductive proof. So we'll do reverse induction on depth. Depth of u. So what is the base case? The base case is in the leaf, the deepest place, right? Which will be actually be, yes, in the frontier, right? So which means u itself is the place where degree jumped from something smaller than m to m or more than m. So u is the deepest. Which means that u is in Fm, which would then mean that if you look at the RHS, so that sum so in the sum w can also be taken as u, so that will give you this plus the other w's. Now obviously the first summoned is just u, and what about the other summoneds? So since both u and w are frontiers, right, we have this, yeah, we have this observation here. So they are all 0. So this is equal to just u. So that is done. Okay. So that's the base case. Now the induction step will be working with addition and multiplication gates. So if you are adding up, u is an addition gate. So in this case, u is the sum of its children, and each of the children follow the identity. So let us write that down. So u1, what is the degree of u1? Degree of u is at least m, but degree of u1 may not be at least m. It's maybe something smaller like m prime. but u2 will have degree at least m. Yeah, so here we can use fm. So now what? Yeah, I wanted to sum. So if this LHS was also, if it was the same W, then I could have summed up. Otherwise, I have this leftover portion. Hmm. Yeah, so maybe your idea of homogenization was,
But then D can
yeah, homogenization can be expensive. I see. So is there an easy fix here? If u1 has less degree than u2, which is equal to degree of u, the lemma, in the lemma statement we are talking about frontier smaller than. Yeah, so maybe this thing is unnecessary. Maybe we just expand it by m independent of u. We just, in frontier expansion, we use m as a parameter. Could try doing that.
But then if so your index it has to be strictly less than m, right? And then so W will go below that frontier rate, right? So that portion should be 0. So so suppose degree of u1 is smaller,
Mm-hmm.
right? And W is, so if it happens that, so it only makes sense when the degree of u1 is greater than degree of W, otherwise it is 0.
So you are saying that if in the case when degree of u1 is less than m, that's the bad case.
Yeah, degree of u1 is less than m.
Uh-huh.
And when degree of u1 is less than m,
But degree of w is always.
no, degree of W is also less than m.
Mm-hmm.
But I'm saying that but W belongs. The thing is, if we change, if you allow M to be a parameter,
Mm-hmm.
in our induction step, we'll also have to show that this holds for all M. Yeah, I think for all M.
But that is true.
But I want to step.
Yeah.
If the W does not
No, but then we are just saying that it only in an addition gate it only holds for all M up to the minimum of the 2 degrees.
No, I think that this probably is unnecessary. Let me remove this. Let us just expand u with respect to fm. Yeah, u and m are given. Let us just think of frontier expansion lemma as expanding u with respect to fm.
But to u, if you add some low, suppose you have a u that has high degree,
Mm-hmm.
and now you add like this really low degree term, then u will change, but the other side of the lemma will remain unchanged, right?
Yeah, no, so actually I have to, m has to be smaller. If I take m to be bigger than the degree, then this RHS will just be 0. There has to be something below. Okay, so no, let me just erase this. So we have, let us look at the RHS. That's summation. So this is equal to which is equal to so for addition gate, the RHS in the lemma statement we can expand like this. Yeah, but then I have to show that this sum is U. Is
We have homogeneous circuit.
And then, of course, yeah, but we can't homogenize because the degree we want
hmm.
can define. So if we homogenize, then there will be in the size of circuit as well.
Yeah, so okay, so then I have to go back and change the theorem. Yeah, otherwise I think I am stuck here. So then let me take back the big claims. Let us just be happy with poly SD size. Yeah, so if I am willing to spend poly SD size, then I can as well make my polynomial and circuit to be homogeneous. So I look at homogeneous parts of F and I prove the theorem, the depth reduction only for the homogeneous parts, and which will then summing up will give you also low depth for the original F, right. So let me add that assumption here. F is homogeneous and C is a homogeneous circuit. Let me go through the proof with this assumption. Then I mean, if later on I find that there is a stronger proof, I'll tell you. Okay, so for now, let us just continue using homogeneity. So in the homogeneous case, the place where we were stuck, yeah, now it will be fine because you know that degree of U is the same as degree of U1.
Poly's log D is not even possible, right? For example, if you take x to the n, what you are
I think it's
claiming is
Sn log.
log D.
X to the 2 to the n. No, intuitively it should be possible, but let us proceed. There is no counterexample for that. It's only in this proof where we are getting stuck. So anyways, with homogeneity, addition gate also has to be homogeneous. So it will be adding up gates of the same degree. In fact, U1, U2 are homogeneous of the same degree. Okay, so all these degrees are the same. So the sum will actually be, I mean the frontier expansion for u1 will be with respect to fm, that is allowed, and for u2 also frontier expansion with respect to fm is allowed. Okay, both of them are allowed, and this then comes out to be u. Well, because let me write the step. So the first thing is by induction hypothesis u1, and the second thing is u2. Is that clear? So we are using the lemma on the first part, on this part, that will be u1, and when we use the lemma on the second one, that will be u2, and the sum is by definition u. So RHS equals u. Okay, this expression that we started with is in fact u. Is that clear? Okay, and in the same case, what is u quotient v? So the other identity in the lemma statement. So that is u1 quotient v plus u2 quotient v by the axiom of quotienting, and now individually you can use induction hypothesis to get u1 w wv plus the symmetric thing. And which you can again, I mean, take the summation out, take w quotient v common, and you will get this equality. Okay. So both the identities in the lemma statement are done in when you use a addition gate.
u1 if degree was less than u1 quotient w 0.
Then you cannot use induction hypothesis. You cannot complete the proof because the RHS, I mean this red part which I am calling RHS, this is then just equal to u2 quotient w cross w sum. Which is equal to u2.
Not u1.
Yeah, so you don't even get u then. You get only a part of u. Well, which is also, in a way, it is intuitive, because if you are using frontier gates whose degree is higher than u1, then expanding with respect to them can never give you u1. So you will actually only be able to compute u2. So it's a fundamental problem in this proof method. So I had to change the theorem statement. Let us prove the weaker version first. Second case is that of multiplication gate. So meanwhile they are trying to prove the stronger version. So we'll have something at the end of the class. So in the case when u is a multiplication gate, since the degree of u was at least m, you know that u2 has degree at least m, right? Because the circuit is right heavy. No, that I cannot say.
If the degree of u2 was lesser, then u would be the frontier. But we've already taken care of that case in the base case. So we can assume that u2 does not have.
Yes, that is what I wanted to say. So let's write that down. So in the non-base case, U is not in FM. So, not being in the frontier means that the right child degree is at least M. This is not the first time that the degree crossed M. So, degree of U2 is greater than equal to M. Okay, so we'll need this conclusion. So now since the degree of U2 is at least M, we can intuitively, when you use frontier gates from FM, they will be able to give you U2. That would be enough in the induction step. So U is equal to U1 bracket cross U2 bracket, which is equal to U1 cross. So U2 now you can expand by frontier, that is allowed. And can you bring U1 inside? So if you bring U1 inside, you can multiply it with U2 quotient W and get U1 U2, which is U. That's again an axiom of quotienting.
So what about the cases when the degree would dip and then again rise up? In that case, U2 would, the degree of U2 would be less than.
Hmm. Okay, in the non-base case, U is not a frontier, but
In the homogeneous case, the degree
Uh-huh.
is monotonically, right?
yeah, so we are using homogeneity here as well. And this is equal to U, right? So that is our first identity in the lemma statement, and let us simultaneously prove the second identity. So in this case, when you take quotient of U1 times U2, you will divide U2. And now you can use induction hypothesis. So that will give you, with respect to frontiers, and when you bring U1 inside, you will get the result. Okay, so that's the form as claimed. Right, so this completes the proof of frontier expansion lemma. Okay, the import of this, all these calculations, is simply that a node U can be expanded by frontier gates of smaller degree, at smaller degree. Okay. So just the frontier gates are enough, nothing else is required, as long as you are doing this at a degree below or at most U. And you can also do the same thing with quotienting, U quotient V. So using this, we will now see what the circuit C prime is. Okay, so C prime will have these U and U quotient V as nodes, and it will be using frontier expansion lemma to do things faster in terms of depth. So in a way, it will be faster, because in the original circuit C, between U and the frontier gates, a lot of extra calculations may have been happening. All those will be now optimized by this frontier expansion lemma identities. So in one shot, you will be jumping from to high degree. Yeah, but still, I mean, it will have some technicalities, so we have to go through that. It's not straightforward. So we'll use this lemma to write the depth reduced circuit C prime. So we'll take a top down approach. Well, which is what the frontier expansion lemma already suggests, that expand U with respect to the frontiers, come down, and then proceed inductively. So we'll recursively compute U and the quotient from nodes in C. Of a lower degree. But M in the currently M is actually a parameter. It is any number below degree of U, right? So you now want to fix M. What should you fix M as? As half. So let us fix M to be half of the degree of U. Right, because we are interested in optimizing the depth. So let us look at the frontier, which is exactly half degree or around half degree of U, expand with respect to that. So this frontier expansion lemma will in a way be doubling the degree. Yeah, so let us fix M to be that. So let f of U be the new notation for frontier. So this is frontier of U at M degree of U by 2. So that's what we are defining. That's f of U. So degree of U by 2 may also be half, right? And or it may also be 1. So I mean, so this will happen when you are looking at really things close to the leaves. So that part you handle separately, make that your base case. So we can assume that this is greater than 1. So that doubling really happens. I mean, you are above 1, and then when you double, you will get 2 bigger integers. So M is an integer bigger than 1, or at least 1, and when you use frontier expansion lemma on U, you will get that identity. W frontier of U, and And you know that W is a multiplication gate, right? So let us further expand this. So U we have expanded as sum over the frontiers of U of these three gates, their product. So let us just write down what we have got here. So U we have written as an addition gate, with fan in less than S. I mean, in this summation, the number of summons is equal to number of frontier gates, and that cannot exceed the size S. These multiplication gates, which is this part, each summoned is a multiplication gate of fan in only 3. And these input multiplication gates, so these multiplication gates, they have, what is the degree that you see here? So U quotient W, WL, WR. What is the degree upper bound on these? Correct. So how do you get this for U quotient W? Right. Since we have taken M to be half, the quotient has degree upper bounded by the difference. So that is half of degree of U. For W, since it's a frontier gate at M, degree U by 2. Left and right, both of them have right. So W was a multiplication gate, so its children cannot have degree more than that. So all of them have degree U by 2. Okay, so this you should think of as something happening inside circuit C prime. So there is a node bracket U, which is an addition gate with lots of inputs, each corresponding to a W in FU, and each of these are actually multiplication gates with only 3 inputs, and these 3 inputs are the lower U quotient W, WL and WR gates. Okay, so we have developed this sigma product layer of C prime by one application of frontier expansion lemma. So the input to this sigma pi layer is of a low degree, which at the output doubles, right? So this is exactly the progress that we wanted, doubling of the degree. So does it mean we are done? Why not?
So but you quotient will be you should, because here you have.
Right. So to complete this inductive proof, we now have to, so we have analyzed bracket U. Now we have to do the analysis also for U quotient W type of things, which appears here. So what is the equation, frontier expansion lemma for that? So for that we will need frontier of this type. Let me define frontier of U comma V to be Fm for So this will be the frontier for the frontier expansion lemma of u quotient v, right? So you are given u and v. What should you fix your m as?
degree u minus degree by 2, because quotient has degree u minus degree v.
No, so u in the tree of u, there is somewhere there is v, and so the w's should be in the middle, because in the frontier expansion lemma you get u divided by w and w divided by v. So w, yes, so it's the average. So let us take m to be average. So average is just degree of u plus degree of v, which is actually also degree of product, half. And let us expand with respect to this. So this is an allowed, this is a legal expansion. So what you get is this, and just following the previous, the calculation above, we want to now see doubling of degree here. So this will be our snippet for u quotient v in C prime. Okay, so the gate u quotient v, how is that being computed? Again, as 2 layers, one for sigma gate and the other for sigma layer, other for multiplication layer. So we can immediately write with respect to WL, WR, because W is a multiplication gate being a frontier. So that would mean WL outside and WR quotient V, right? We get these three things. Now are these three things, is the degree less than half of degree u quotient v? So the problem is actually, if you look at this WL, what is the degree bound that you have? M, right, which is degree of u plus degree of v half, but that is more than degree of u by v, right? So this is the gate which is which may have actually degree more than half of the degree of this. So we cannot stop here. I mean, we have to develop C prime more so that this problem is corrected. So degree of WL could be more than degree of u quotient v by 2. So what should we do?
Wait, how can that happen? The degree of W is
Yeah, it's negative. So we have defined, we were actually forced to define M like that. It should be between u and v. So we picked exactly in between. But then the place where it hurts is in the LHS you have u by v, which has degree as difference. So difference may be smaller than the mean. Mean by 2. Oh yeah, the difference can be small. This is well, difference by 2 can be smaller than the mean, which actually usually it will be. So we have to, so whenever stuck in such a situation, we'll use the only thing we know, which is frontier expansion lemma. So we'll expand WL by another application of frontier expansion. So we apply frontier expansion lemma again. So that will give us a big sum. So u quotient v is Now W we already had, and for WL look at the frontiers. So this will be, you have U quotient W, U by W, you have now WL by P, P left, P right, and WR by V. So that's the thing which is new, the red thing, that is the frontier expansion of this single node WL. So now we have 5 things instead of 3. And what can you say about their degrees of these 5 things? So degree of U by W is upper bounded by degree of U minus degree of W, which is the mean, which is half of what we are computing. That is fine. Degree of WR over V is smaller than the mean minus degree of V, which is again half of what we are computing. In the red part, we want to claim that degree of WL by P and PL and PR, they are all smaller than this. So this we have to check. So why is that? So remember that P is here. Right, so it is expected that WL over P and P both will have degree. So there's at most degree of WL by 2, and degree of WL will be smaller than degree of UV. That would be the proof.
Why is the degree of W?
Well, WL may not be half of the final thing, but it cannot exceed that degree.
Wait, can we go to the previous slide? I mean, that was the point, right? WL could be greater than degree U minus V by 2, which is where we start.
Not by 2. I am just saying that degree of WL is at most the degree of LHS. There is no half. So that's a simple demand. Okay, so as an exercise, show that degree of WL is less than equal to degree of U by V. That's all. So since that is true, and on that WL we are doing frontier expansion, so WL by P will now be bounded by degree WL by 2, which is then smaller than half of the final thing. So now we have a perfect case of, I mean, we have this snippet, this part of C prime where there is a big sum, feeding, which is in which you are feeding multiplication gates, and these multiplication gates have fan in only 5. So this is the bound you get. You get that fan in of multiplication gates is 5, fan in of addition gates is unbounded, and whenever multiplication happens, degree doubles at least, right. So you get all these structural properties which imply the theorem.